All right. I thought golf was Thursday, Friday, so I don't know. Okay, so this section is using a calculator with Trig, and then also graphing Trig. So, yeah. Okay, so for question or example number one, it says we're using a calculator. Okay, so again, I'm using my 84 because I'm familiar with the 84. If you want to try to figure out the Inspire, that's fine. So anytime we're working with Trig, we got to be careful of the mode that our calculator is in. So for letter A, do you think that 2 is giving us a radian or a degree value? A radian, good. Okay, so generally, if they don't say or give the degree symbol, then it's usually in a radian. So make sure your calculator mode is in radians. And if you hit the sign of 2, do you get 0.909? Yay, nay, anybody? Good. Okay. And then if I do the tangent, so tangent is going to be negative pi over 5. So again, we're still in radians because it doesn't give us an actual degree symbol. So I got negative 0.727 for that one. Everybody good there? That's pretty straightforward, pretty simple. Good. Okay. All right, so example 2, it says use a calculator to find the missing measure. Oh, sorry, I didn't even see a C. My calculator was covering it. Sorry, thank you. Okay, so secant is not a button, so we have to use its reciprocal. Yeah, good. So 1 divided by the cosine of 1.3. Yeah. So remember, you're always going to round to 3 decimal places. Anytime you're getting a decimal of any kind in AP Calculus, they tell you to round to 3 decimal places. All right, for example 2, we're looking for the x. Okay, so this time they're giving us a radian. They actually label the radian. So which SOHCAHTOA piece, which trig ratio are we going to use? We got opposite and hypotenuse. Good, so sine would be the sine of 0.5 equals 5 over x. So when my x is in the bottom, what do I have to do? Good. So multiply it out. So we're going to then divide by the sine of 0.5. So x is equal to 5 divided by the sine of 0.5. Did anybody else get 10.429? Yep. Oh, that's a good question. I would say if it's a calculator portion, I would put it into decimal. But if it's not a calculator portion, then you could probably leave it. Yeah. Right. Yeah. I mean, it could be the sine of 1/2, so you could potentially use your unit circle to figure that out. So maybe. So it would probably be what, a square root of 3/2 in there. Well, no, actually, I take it back. 1/2 is not an angle on there. So you definitely could not do that without a calculator. All right, so this time we're looking for theta. Okay, what trig ratio are we using if we have the opposite and adjacent? Tangent. So tangent of theta is equal to 2 over 5. So how do you find the angle? Good, inverse. Good. And remember that notation, the inverse is notation. It's not an actual exponent, which is confusing, I think. So 0.381. Okay, so this is going to be, I'm going to put a little r right there because we're in radians, right? It doesn't tell us to go to degrees or anything, so I just kind of assuming that everything has been in radians so far, so I'm sticking to radians. All right, so we're gonna start looking at the graphs of our trig functions. Okay, let's just go down to the graphs. How about? Okay, so let me write this first. So, do you guys remember that generally, whatever you have is like, so it doesn't matter what trig ratio or what trig piece I'm doing, it's always going to be bx plus c and then plus d. Okay, so the d is always going to be our up and down shift. The c is going to shift left or right, but the b is going to affect it. So we'll talk more about that in a second. But for the most part, the b is important because it tells us about the period. Okay, so the period is one cycle or one full revolution. So what that means is if I have a sine curve, right, a wave that just repeats and repeats and repeats, a cycle is one piece that does not repeat. Okay, so if I start to repeat, then I'm doing additional periods. Okay, do you guys remember where the sine function starts? At the origin, good, yeah. So it starts at the origin. Okay, it does have a period of 2 pi, okay, which means it's going to do one full cycle and end at 2 pi. So it's going to cross right at pi. The amplitude is 1. Okay, I'm going to even say the amplitude is 1. Okay, so that means the height of those waves goes up 1 and down 1 from the midline. Okay, for cosine, do you remember where cosine starts?
It starts at 1.
At 1, good. So yeah, so again, the period is going to be 2 pi. So that means that if I start at an amplitude height of 1, when I'm finished with my wave, I have to finish at the same spot. Okay, so at 2 pi, it's going to have the same height. Okay, so that means halfway in between, it's going to hit a minimum. And then basically cross the x-axis between those existing points. Okay, so the cosine, for the most part, when we draw one period, is going to appear to look like kind of a U curve. Okay, so do you remember what cosecant looks like? Okay, so cosecant is basically a reciprocal of the sine function, right? Okay, so basically what we would do is we would take every x and y point. So at this point right here, 0, 0, we flip it. Okay, so at 1, the y value is 0, so it'd be 1 over 0. Okay, so if I have 1 divided by 0, that's a problem, right? So what happens on a graph if I divide by 0? Not a hole, but a vertical asymptote. So let's see, I'll use red. Okay, so the cosecant function basically kind of, if you think of it, maybe starts at the same place as the sine function. So the first location that we consider is at 0, there's an asymptote. Okay. The period is still going to be 2 pi for this. Okay, and then basically every time that function, our sine function, touches the x-axis, there's going to be another vertical asymptote. Okay, so when I look at this original function right here, I go, oh, there's another vertical asymptote, and that 2 pi is another asymptote. Okay, so there and there. Okay, and then what happens with the parabola is it basically gets cut in half and then it reflects upwards. Okay, so instead of having the sine curve, it creates little parabolas. Okay, so the parabola, the first parabola, yep, the first one goes upwards, and then the second one goes downwards. So this would repeat infinitely in both directions. So I would still have these vertical asymptotes continuing on forever and ever, and these parabolas would alternate every asymptote. Does that make sense that this continues forever? Okay. So cosecant and secant functions really look quite similar. I mean, they're the same function, it's just a shift. Okay, so secant is going to be very simple cosine. So where is the secant function going to have those vertical asymptotes?
Negative sine.
Yeah, so the first one on our cosine function that hits 0 is at pi over 2. So it's pi over 2, 3 pi over 2. You can go in the negative direction if you want. I actually like to go in the negative direction on this one, because the first parabola is going to be upwards and it's going to cross right through the y-axis. Oops. So maybe before I progress, let's talk more about those vertical asymptotes and where we find them. Okay, so on the cosecant function, the vertical asymptotes. Okay, so if I was going to find the very first vertical asymptote, where would you say it exists? You're close. We're going to do how far apart. That's where you're going to use your period. But where does the first vertical asymptote on the cosecant?
The origin unless it's a horizontal.
Yeah, so it's going to start right at 0. So we're going to say, unless this function is shifted to the right or to the left, okay, the first vertical asymptote will always go through 0. Okay, so first one is always at 0, and then so if my period is 2 pi, it's going to be whatever your period is divided by 2. Okay, so this is going to be really helpful when we have period changes and shifting going on. Okay, for the secant, where would you say the first one is? Okay, yeah, that one's kind of hard to say. Like, okay, if I was going to do this in terms of our period, so if our period on this is 2 pi, okay, you want to say that this is our first one?
Yeah.
Okay, so if this is our first one, this is the negative. Okay, and then how would I say, so this is half, 1/2, right? Half of pi. How would I compare 2 pi to half of it? Close.
Minus
It's not a half. Half would be here. Quarter. So 1/2 is a quarter of 2 pi, right? 1/2 of a pi is 2/4 or a quarter. So I would say negative. Take the period divided by 4, and then the asymptotes have the same distance as our secant or cosecant function. So they're a distance of half of a period. Does that make sense to everybody? This is our first asymptote, right? We'll go with purple for tangent. Okay, do you guys remember what tangent looks like? Good, John Travolta. So basically, you're thinking about they're separated by asymptotes. The first John Travolta goes straight through the middle. Okay, so if you look at this really closely, they changed the scale. Okay, everything else ended at 2 pi, but on tangent they ended at pi. Okay, so the period for tangent is going to be just pi. Okay, so that first asymptote is going to be at pi over 2 and negative pi over 2. Sorry, every time I put my hand down, it shifts. Not to do that. Okay, and you can even get really specific. That point right there is always going to be at the height of the amplitude. So it's kind of like a quarter in between those asymptotes. So this y value has a height of your amplitude. Okay, so if we talk about our vertical asymptotes, where would you say the first one is? So if my period is pi, okay, our first one is at pi over 2, so what's the comparison between pi and pi over 2? Half. Okay, so I would take my period, divide by 2 to find it. Okay, and how far apart are they? The full period. Good. Okay, so cotangent is going to look like tangent but slightly different. Do you remember the difference? What's that? It does not. So again, the same rule applies. It's a reciprocal. So any place that our tangent cross the x-axis is going to be a vertical asymptote on my cotangent. So my first vertical asymptote will be at 0. Okay. They will be still the same distance apart. Yeah, and then also he's flipped upside down. So the John Travolta, that was hard to draw. He's got his left arm up. Okay, so this has a period of pi for the vertical asymptote. What would you say the first one is? Good. Perfect. Okay, so when I look at the vertical asymptotes, just for a reference, I always remember that if the function has a vertical asymptote and it starts with the letter C, the first vertical asymptote will always be at 0. So the other two are slightly different things, so they both have the same, but C starts at 0. I always remember that. Okay, so okay, so these are all giving you the same form. Okay, so you should know that the period for sine, cosine, secant, and cosecant. So notice those are all the yellow functions. They all have the same period, 2 pi divided by b. Okay, tangent and cotangent, the John Travoltas, are pi divided by b. Okay, the amplitude is how high the wave is. That's always the a value in front. Here is a big thing. I have rarely seen this form where they use two sets of parentheses. Okay, so if you have two sets of parentheses, then you can say, oh, but this function is to the right C or left C. Okay, but if it has been distributed, where it's most likely going to be written like this, okay, that horizontal shift is going to be effective. Okay, so if there's only one set of parentheses, you have to do C divided by B to get the true horizontal shift. Okay, that's a big important piece. Do you guys see the difference between those two forms? The two sets of parentheses where it pulls it out. I like the first one, second one is mean. All right, should we give it a go? Let's do it. Okay, so without using a calculator, we're going to sketch it. The nice thing about this is I love that they give us the scale. Or actually, I don't know if I love that. We'll find out if I like it or not. So we're going to list all the things. Okay, so the first thing we want to list is the period. Okay, so if I'm working with the cosine function, period is 2 pi divided by b, right? So in our case, what is the b value? Huh? What are you saying? What? 1/2. Are you guys following me? Sorry, did you say what? Okay. Are you good though? One, oh, 1. Okay, so if you have 2 pi divided by 1/2, remember dividing by 1/2 is the same as multiplying by the reciprocal. So what's 2 pi divided by 1/2? 4 pi, good. So our period is 4 pi. Okay, I do also want to list the amplitude. What is the amplitude? So the amplitude is the value in front of the trig function, so 5. Yeah, so I'm going to say 5. Technically, it's always an absolute value. It's always a positive. But what does the negative do to our function? Flip. Okay, so it is flipped over the x-axis. Okay, so when I go to draw this, I'm going to say, okay, I'm drawing a cosine function. Okay, so usually the cosine function looks like a U, starts at the amplitude. Okay, but it's been flipped upside down, so where is it going to start at? Good, -5. So we have no right or left shift, which I appreciate. So that means it's going to end at the distance of the period away at the same height. So where's it going to end? Good. So that's the bottom of our U. So where is it going to max out at? What exact point? Good. 2 pi 5. So to get there, it's got to cross the x-axis exactly at pi and 3 pi. Okay, so make sure you're drawing a wave and not a V, a sharp tooth. All right, that one wasn't bad. I like that one. All right, let's try B. So B, this is the scenario where we have the phase shift. It's going to shift to the right or to the left. Okay, so let's go slow. Let's go. What is the period? Period is 2 pi over B. So our B value in this case is 2. So the period is going to be pi. Let's list the amplitude. What's the amplitude? How high and how low is our wave going to go? 1, good. Okay, and this time it is going to shift to the, which direction? If I have minus, it's going to go good to the right. And so remember, this is when I have to do C divided by B to find the true shifting. So good, pi over 2 divided by 2 is pi over 4. So we're going to shift this thing pi over 4 units to the right. Okay. All right, so I'm thinking sine function usually starts where? At the origin. Good. So I'm going to basically kind of start my little spot at the origin. Then I have to shift to the right pi over 4. So this is going to, so pi is going to be 4 increments, right? So pi over 4 is going to be 1 increment to the left. So right there. Okay. And then I want to, my drop. Oh, right. Sorry. To the right. Thank you. Good catch. Okay, so then I have to finish the distance of my period away. Okay, so my period is pi. Okay, so if I look at my scale, the distance of pi is 4 increments. So I need to finish 4 increments away. Okay, so I should finish right here, 1 increment to the right of pi. So where is my next cross, x-intercept? Since I'm drawing an S-curve. Good, it's right in the middle. I'm going to max out at pi over 2, 1, right? Pi over 2, 1. And min at pi, negative 1. Pretty easy, not too bad? Good. All right. Okay, so the sine and cosine functions are related to the Pythagorean identity. So Pythagorean's theorem, hopefully that looks pretty similar, right? So usually you see x squared plus y squared equals r squared. So if you think about like the unit circle, the x is the cosine, right? So cosine squared plus the y squared, that's sine squared. And on a unit circle, what's my radius? 1. Wait, say that again? Oh. No. So you're saying that cosine squared is equal to sine squared, cosine squared? Oh, an identity? I don't think so. Not that I recall. But we're going to use the Pythagorean identity to reduce this. Okay, so we're going to solve this equation like we did in the last lesson. Ooh, I don't like purple. Can you see that? Okay. Anyways, the reason that this equation is gross is because I have 2 trig pieces in there. I have a cosine and I have a sine. Okay, we cannot solve a identity if there's 2 trig things involved. So what I need to do is rewrite it. So I'm going to use a Pythagorean identity on the sine squared piece. Okay, so if you go back to your Pythagorean identity and go, okay, well, I want to replace the sine squared. Okay, well, I don't have the sine squared on either. Okay, if I go back to this and go, okay, I want to isolate sine squared, how would I get rid of the cosine squared? Subtract it. So do you agree that sine squared, I'll use theta since they're using the theta, is the same as 1 minus the cosine squared of theta? Okay, so what I'm going to do is I'm just going to substitute that piece in. You got to be careful because there's a minus sign in there. So I'm going to go 2 cosines of theta minus 1 minus cosine squared of theta, yes, equals negative 2. So what do you think I would do at this point? So what kind of function do I have? It's a little hard to recognize. But there's it's a quadratic. Okay, so technically what I'm doing is I'm solving a quadratic that's in terms of a cosine. So I'm going to treat it like a quadratic, and I'm going to set it equal to 0. Okay, so first I'm going to distribute the negative through that quantity, and then I'm going to set it equal to 0. Okay, and we do want our x squared term, or in this case our cosine squared, to be positive. So we're going to keep everything on the left side. So we'll just add 2 over. So I'm going to put this in the correct order. So cosine squared plus 2 cosine plus 1 is equal to 0. Okay, so if you think about this, think of it as x squared plus 2x plus 1. Okay, so this is kind of like the same idea, right? Bless you. How would I solve that if this was equal to 0? Good, it factors, right? So can I write x plus 1 and x plus 1 is x plus 1 squared? Okay, so that's exactly what we're going to do with our cosine equation. So this is going to turn into cosine of theta plus 1 squared. Okay, so what would you do from there? So I got to get rid of the square. How do I get rid of the square? Square root. Okay, the square root of 0 is 0. I like that. Then I'm going to subtract 1. Yep. So this is where I now grab my unit circle. I'm looking for the cosine, so I'm referencing which variable? X. So where on the unit circle do you see the x value is a negative 1? Good there? That one makes sense? Yeah, that one's not too bad. I mean, it could be a lot worse, but oh yeah. Not in this class, but it's code of deriving.